So in the last lecture we have discussed some concept about voltage sensing amplifier, that is differential voltage sensing amplifier. I have rewrote that circuit, and from that lecture we have concluded two important points. One is if the value of V bit, that is gate voltage of M1 increases, the output will increase. At the same time, if the value of a V bit bar, that is gate voltage of M2 decreases, it also results in an increased output. That means there will be a relationship between output and input. Now we are going to define the relationship between output and input. The best way to define the relationship between output and input is obviously defining the gain of that particular circuit, that is AB. So we have to define the gain of the differential amplifier used here. So we are not going to the mathematical derivation of gain, but I am going to define the gain as transconductance of input transistor times RD. So simple method to write the gain as transconductance of input transistor times RD. So here the input transistors are M1 and M2. These two are NMOS transistors. So I am going to, and we are considering that these two transistors are identical in all aspects. So I am going to represent the transconductance of input transistors as GMN because it's an NMOS transistor times RD. RD is obviously a resistance. We are going to define what actually this RD is. RD is nothing but RF parallel RD. You can simply define RD as RF parallel RD. What is RF and what is RD? So if you are at this node, that is V out node, RF is the resistance seen while we are looking towards M4, that is in the upward direction, that is RF. R down is the resistance seen while we are looking at the downward direction. So RF means the resistance seen looking upward, and R down means resistance seen looking downward. So this can be written as GMN into R up parallel to R down, or R up parallel to R down. Okay. So RF is resistance seen looking upward. What will be the resistance looking upward? It will be the resistance of M4. So I am going to label it as GM1 into RF is resistance seen upward. Resistance seen upward means RO4 parallel to resistance seen downward means RO2. Simply this will be the equation for gain. So simply you can define gain as transconductance of input transistor times RD. RD is RF parallel R down. From that we have derived the equation for gain as AV is equal to GM into RO4 parallel to RO2. Then what actually this gain is? As you all know, gain AV can be written as the ratio of V out by V in. So from this, what will be your V out? V out will be equal to gain AV times V in. So from this circuit it is clear that this V out is the output voltage, but V in, we are giving input to the two transistors. So V in will obviously the difference voltage between first transistor and second input, difference of input voltage between first transistor and second transistor. So what will be this V out? So V out will be equal to AV into V bit bar minus V bit. So this will be your output. In another way, you can define this same. So I am going to represent this as V out, V out 1. So we can also define V out as V out 2, which will be equal to AV into. The only thing that you should keep in mind is that the input should be the difference input. So it can be also written as V bit minus V bit bar. Both are same. Only difference between these two things is that there will be a change in sign if you are considering V bit minus V bit bar minus V bit and V bit minus V bit bar. So in some cases we will define this gain as AV is equal to minus GMN into RO4 parallel to RO4 because it will depends upon on which basis we have defined the input, whether it is V bit bar minus V bit or V bit minus V bit bar. This one will be the gain of this differential pair. And one thing that you should keep in mind is that what's the advantage of defining this gain is that, or defining a circuit like this is that, because we can simply control the gain of the entire circuit by changing this GMN. Then how will you change the GMN? GMN can be changed by changing the width of the transistor or by changing the bias current.